our pleasure to have here Anna Bokulic, who will speak about nonlinear electrodynamics and introduction.
So yeah, this is the first part of this short course. So today we will go through the introduction to nonlinear electrodynamics. So we will briefly discuss the motivation behind nonlinear electrodynamic theories. We will go through the examples from the literature. We will discuss their properties, and also we will highlight the differences compared to standard Maxwell electrodynamics. So to do so, we will start with a short review of Maxwell's electrodynamics. So here it's important to stress what do we exactly mean when we say that Maxwell's theory is linear, and what are the consequences of this linearity. So as you can see, Maxwell's Lagrangian, it is quadratic in the electromagnetic 2 form F. And the equations that stem from Maxwell's Lagrangian, they are linear. Here I wrote the vacuum equations. And so with this linearity comes superposition principle. So this means that if we know one solution of Maxwell's equations and we know another one, their combination will again be the solution of the system of equations. And of course, when we move on to the nonlinear case, this feature will be lost. And Maxwell's theory has another two properties, which are conformal and SO2 duality invariance. We'll discuss them a bit more in the context of nonlinear theories. So for now, I will not go into details. And on the right side, you can see the original form of Maxwell's equations as they appeared in the paper. So here I find it interesting how important the compact notation that we have today is actually, is relevant. And so if we want to discuss Maxwell's theory in the context of general relativity, we need to find the exact form of energy momentum tensor. So we can derive it by varying the action with respect to the metric tensor. And here what you can notice is that the trace of Maxwell's energy momentum tensor vanishes in four-dimensional spacetime, and this is exactly the manifestation of the aforementioned conformal invariance. And also, Einstein-Maxwell theory is a well-studied subject. So here, a lot of solution-generating techniques have been formulated and successfully applied to generate solutions of Einstein-Maxwell system of equations. Here I single out the Reisner-Nordstrom solution, which corresponds to static spherically symmetric black hole. Its metric and gauge potential are written here. So the metric and the gauge potential. And one of its features is the presence of the central singularity, as you can see if you calculate the Kretschmann scalar. And the singularity is shielded by the event horizon. Now it's natural to ask, why do we need to go beyond Maxwell's theory? So it is very successful in many domains, but there are regimes in which it breaks down. So for strong electromagnetic fields, the nonlinear effects will come into play. And there is evidence from quantum field theory that the electromagnetic interactions, even in vacuum, become nonlinear. And this may also lead to new phenomena which cannot be accounted for in Maxwell's case. So, and NLE models, they may capture this idea effectively. Also, another thing that appears in Maxwell electrodynamics is the fact that the electric field of a point charge, it will diverge as radial coordinate goes to 0. And then consequently, if one calculates the self-energy, it will be divergent. And certain NLE models may provide the framework to regularize such singularity. And also, this is not the main motivation, but we have seen that the black holes in Einstein-Maxwell theory will be singular. And it was noticed that some NLE models may lead to regular black hole spacetimes. We'll discuss that in detail tomorrow, what exactly the limitation to this idea actually are. So, to sum up, there is both empirical and theoretical motivation to introducing nonlinear electrodynamic theories, and they both lead to some novel physical predictions. And also, if you have any question during the talk, feel free to just interrupt. It's welcome. And now, just to put NLE theories into some historical context, so 1930s can be regarded as the decade in which NLE theories were born, and the two earliest models were Born-Infeld and Euler-Heisenberg theories. We will explain them in a couple of minutes. And then in the late 20th century, NLE theories gained some attention in the context of applications in gravitational theory and also string theory. And so what ignited the interest here was the fact that a particular regular black hole solution was interpreted in terms of an NLE theory. So actually, the source was identified with a certain NLE model. And also, it was noticed that Born-Infeld Lagrangian appears as a part of the effective action in some string theories. So the applications of NLE theories are diverse. Of course, in this course, our focus will be on the applications in gravitational theory. And here, the important aspect is black hole physics. So when NLE models are coupled to gravitational action, one gets various new black hole solutions, which can have properties that are very much different than the black holes from Einstein-Maxwell theory. So, as I mentioned, one can get regular black holes in certain scenarios. And also, since the electromagnetic potentials and charges, they appear in the fundamental laws of black hole thermodynamics, it's also important to see how does the presence of NLE fields affect these laws. Also, one may consider NLE fields in modified gravitational theories and again search for some novel solutions. They're also relevant as a part of string theories and also in the ADS CFT correspondence, especially a particular segment of it that is gravity condensed matter correspondence. When it comes to cosmology, it was noticed that certain NLE theories, when coupled to cosmological metrics such as Friedman, Robertson, Walker, the initial cosmological singularity may be absent, and also certain NLE models may account for the accelerated universe expansion. In terms of the applications in astrophysics, Annalee fields might be relevant for the physics of magnetars, which are a type of neutron stars, which have very strong magnetic fields. So at this scale, the Annalee effects may become relevant. And there are also some experimental tests being done, but here it's important to state what is the scale at which NLE effects actually become manifest. So this happens for magnetic fields that are order of magnitude 10 to 9th Teslas, and the electric field that is 10 to the 18th volts per meter. So it's not easy to experimentally test these effects. And there are two experiments, the extreme light infrastructure and PVLAS, that are probing the nonlinearities and the electromagnetic interaction by using very strong lasers. And here you can see the title of a paper published in Nature by Atlas Collaboration, in which they report the evidence for light by light scattering at the LHC. And now, how does one actually construct an NLE theory? So the basic building blocks are two electromagnetic invariants, here denoted by F and G, and this star represents Hodge dual. So one may ask now, what happens if we try to calculate scalars that are formed by contracting more two forms F? Well, scalars that are formed in such a way will always reduce to some combination and higher powers of the basic invariants F and G. So here we do not lose any generality by restricting our attention to invariants F and G. So an allele Lagrangian density can then in principle depend on both invariants. And just to simplify further discussion, we'll sort NLE theories into two groups. So we'll say that the Lagrangian density belongs to F class if it depends on the invariant F only, while if it depends on both of them, we will say that it belongs to the so-called FG class. And so now you may wonder, can we take just any function of invariance F and G that is smooth enough and call it an NLE theory? And from the physical standpoint, the most relevant NLE theories are the ones that reduce to Maxwell's Lagrangian when fields are weak. So to say that precisely, we'll say that the NLE Lagrangian obeys Maxwell's weak field limit if the derivative of Lagrangian with respect to invariant F, here we'll denote it by LF, if it goes to -1 or 4, and if derivative of Lagrangian density with respect to invariant G goes to 0 as both invariants go to 0. So we want to capture the idea that the Lagrangian effectively behaves as Maxwell's when fields are weak. But it's also important to state that there are some interesting theories from theoretical standpoint that do not obey such a limit. And now when we have this general NLE Lagrangian, we can derive generalized Maxwell's equations. And now you can see that the first one, it's basically it's the same as in Maxwell case, because it's not dynamical in a sense that it holds by construction. So the two form F is equal to the exterior derivative of gauge potential A. And if you use variational procedures, so you take the Lagrangian and vary it with respect to gauge potential, you get the second generalized equation. And it can be written in a compact way if you introduce this two form Z, and you see that it contains derivative of Lagrangian with respect to F and both with respect to G. So here it's obvious that we went beyond the linear regime. And again, if we want to consider NLE theories in the context of gravity, we need to derive the energy momentum tensor. And again, what one does, we calculate the variation of the action with respect to the metric. And then you would arrive at this form of the energy momentum tensor. And it's useful to notice that in 4 dimensions, it can be split into a Maxwell-like term. So we call it Maxwell-like because it's equal to Maxwell's energy momentum tensor multiplied by LF. And the second term is the trace term. So it is proportional to trace of energy momentum tensor and the metric G. And this form, as we will see, is very useful when one wants to prove some results, because there are some there's some requirements that will constrain LF and trace T, as we'll see in further lectures. And we'll consider minimal coupling of nonlinear and gravitational sectors. So the total Lagrangian form is just given as a sum of nonlinear contribution, nonlinear electromagnetic contribution, and gravitational contribution. And then we can discuss fields, potentials, and charges in NLE theories. So with respect to a vector field X, we can introduce the electric and magnetic forms E and B, defined in this way. And in the NLE case, we can introduce further two forms, D and H, which are defined as contractions of X with two forms Z and Hodge dual of Z. So in general, D and H will be some combinations of E and B multiplied by LF and LG. And also the two form F, it can be split into the so-called electric term and the magnetic one. And now let's suppose that this vector field X is promoted to some Killing vector field, here denoted by K. And then let's assume further that the electromagnetic field inherits the symmetries of the spacetime, which means that the Lie derivative of F with respect to Killing vector K is equal to 0. In this case, we can show that the forms E and H are closed. So we can see that if we use the definition of forms E and H, and then we apply Cartan's formula, the first term, this Lie derivative term, it will drop because of symmetry inheritance, and the second term, it will vanish because of generalized Maxwell's equations. And then since these forms are closed, and if we suppose that the manifold is simply connected, then we can introduce globally well-defined scalar potentials, phi and psi, which are related to forms E and H in this way. So the exterior derivatives of potentials will be equal to E and H. Yeah. Okay, so it's convenient pretty much to introduce the form H, especially because it will be closed. So in general, form B will not be closed. So in the NLE case, you cannot then introduce the scalar potential that belongs to the form B. That is one thing that immediately comes to my mind. And also, they will, in a way, incorporate the effects of non-linearity, similarly to when you discuss in Maxwell electrodynamics materials. So something like that, an analogy could be drawn. Yeah, yeah. Yeah, yeah. It is analogous in a sense, yeah. And also, one can define Comer charges. So the expression for the electric charge gets modified in the Anneli case. So we calculate it as the integral over to surface S, but now the integral of Hodge-Deal of Z. And the magnetic charge is proportional to the integral of to form F. And then we can start with the examples of NLE theories, starting from Euler-Heisenberg theory. So it comes from quantum field theory. It is one loop QED correction to the Maxwell term. And now if you want to do a full one loop calculation, it's given by this complicated integrals. So what one does here, typically we resort to the effective theory approach. So we consider the case in which the photon energy is much less than the electron mass. So effectively, this loop in which we have electrons and positrons, it is replaced by a point interaction between the photons. So one integrates out the heavy degrees of freedom, which are electrons and positrons in this case. And then what we are left with is a much simpler Lagrangian. And also, Euler-Heisenberg theory can explain then the process of two-photon scattering that we have seen before. The second theory that we'll discuss is Born-Nifl theory, and it was proposed in order to regularize singularities that appear with point charges in Maxwell case. So here you see that it has this dimensionful parameter B. And if you expand it in the weak limit, you can see that it obeys Maxwell's weak field limit. And then we'll show explicitly how does it actually regularize the electric field of the point charge, and we'll also interpret the meaning of parameter B. So now we are in flat space-time in spherical coordinates, and we assume that the form F is of this form, so it has the electric field that that depends on radial coordinate only. And then to evaluate the Maxwell equation, we need a derivative LF. And also what you can calculate, you can check that the invariant F, in this case, it becomes equal to -2 times the square of E. So that is what appears here. And now you can check that the second generalized Maxwell equation will tell you that this combination here is constant. And the value of the constant is fixed by the definition of Comer charge, and it will exactly be equal to the electric charge Q. And of course, if you want to see how does one get this result, feel free to ask. So now we have to solve this equation to extract E, and then one gets the final form of the electric field. And now you can see that it remains regular as R goes to 0. And actually, this parameter B represents the maximal field strength. So by imposing the upper limit, we manage to regularize the field. Born-info, the Lagrangian is invariant with respect to SO2 rotations. So this is a property that it shares with Maxwell electrodynamics. And as I mentioned before, it appears in the low energy limits of string theories. And there, this parameter B is related to the string tension. One of the recent additions to the family of NLE theories was the mod-max theory. And it gained a lot of attention because it is both conformally invariant and invariant with respect to SO2 rotations. So it shares these properties with Maxwell theory. The form of the Lagrangian is relatively simple. You can notice here this parameter gamma. It acts as charge screening parameter in Coulomb solution and also in static spherically symmetric black hole solutions. And here I put the equations of motion for Einstein mod-max systems. Because now if you look at them, you will see that whenever the invariant G vanishes, so if we restrict to either electric or purely magnetic case, or at least if the invariants F and G are proportional, then the theory becomes Maxwell-like. So basically the terms, the LF and LG terms, they will just become constants in this case. And effectively, we have linear theory. And solutions will also exhibit pretty much Maxwell-like behavior. And this means also one another thing. We can adapt solution generating techniques from Einstein-Maxwell theory to Einstein-Mod-Max case. So now to illustrate this point, we can take a look at static spherically symmetric black hole solutions, the electrically charged case. So now here from the metric and gauge potential, you can see the similarity with Reisner-Nordstrom black hole. And you can see that this parameter gamma acts as a charge screening parameter. And here also as an exercise, you can check that by applying the SO2 duality, apologies, I think that I missed one slide. Yeah, we should have explained what SO2 duality invariance is before going to this point. Yeah, so as I mentioned before, Maxwell theory is both conformally invariant, invariant with respect to SO2 rotations. General NLE theory will not share these properties. We have to impose certain conditions on the form of Lagrangian. So conformal invariance translates to the condition that the trace of energy momentum tensor is equal to 0, which in NLE case implies that combination L minus LF times F minus LG times G vanishes, because this is exactly proportional to the trace. And SO2 electromagnetic duality invariance means that the equations of motion will be invariant to the rotations in 2D plane defined by the angle alpha. So in the NLE case, this is non-trivial demand because to form Z, it also depends on F. And you can check that the energy momentum tensor remains invariant to such a transformation, which means that we can then use the SO2 electromagnetic duality invariance as a solution generating technique. So without explicitly solving the equations of motion, if you know the electric solution, you can easily extend it to a dionic one. And the condition that will ensure that the Annaly-Lagrangian is SO2 duality invariant is this one here. So the scalar formed by contraction of Hodge dual of Z with to form Z minus invariant G has to be constant, and this constant vanishes for theories that obey Maxwell's weak field limit. Okay, and now we can move on to this point. So what you can then see from the definition of Comer charges, you can see that this original electric charge Q now gets split into the electric charge term, we'll call it Q tilde, and also the magnetic charge P tilde. And then by applying the rotation, you can calculate this form of novel F tilde. And you will see that these sine and cosine terms that appear, they will be absorbed in the definition of this novel charges Q tilde and P tilde. And now you get F, which contains both the electric field term and the magnetic field term. And what is now left to be done in the metric function, you have to replace the square of the electric charge with the sum of the squares of novel electric charge Q tilde and P tilde. And this will be the solution of the theory. So without explicitly solving the equations of motion, you can generate this solution. And there are other Annaly-Lagrangians that have been introduced over time with different motivations. Here I singled out power Maxwell Lagrangian, which is equal to, it is proportional to the invariant F up to some power S. And it will be conformal invariant whenever this S is related to the spacetime dimension in this way. And then it has been used to construct higher dimensional black holes with this conformally invariant source, because we know that when we move away from 4 dimensions, Maxwell theory will no longer be conformally invariant. And here I also put exponential and rational Lagrangians that we'll discuss more tomorrow. They were constructed in order to give regular black hole solutions, but apart from that, they did not originate from some more fundamental theory, as for example Euler-Heisenberg Lagrangian or Born-Infeld, which appears in string theory. And then one phenomenon that appears in the Annaly case, which is not present in Maxwell electrodynamics, is related to the behavior of light rays. So in the Annaly case, light rays, they propagate along the null geodesics of the effective metric, here denoted by G bar. And in general, it is different than the spacetime metric, G. And the form of this effective metric can be found if we split the two form F into the background field and then some small perturbation. And then we solve the equations of motion by taking into account that this perturbation is smaller than any other relevant scale in the problem. And then one can ask a question, will different polarizations experience different effective metrics? And if the answer is yes, then we say that there is birefringence and there will be two different effective metrics. Now, in Maxwell case, there is no birefringence, and the space-time metric, the effective metric corresponds to the space-time metric. In Born-Infeld case, there is no birefringence, and so there will be just one effective metric, but it will not be the same as the spacetime metric. And in Euler-Heisenberg theory, there will be two different effective metrics, and actually the value is being experimentally tested by the PVLAS experiment that I mentioned before. So here in this image on the left side, you can see three light cones. This outer one, C1, it corresponds to the spacetime metric, and there are two others that correspond to the effective metrics. So this is the case in which there is birefringence. And also notice here that the light cones of the effective metrics are inside the light cone of the spacetime metric, which means that the theory is causal. And on the right side, you can see this case in which there is just one effective metric. So Born-Infeld case belongs to this right side of the image. And so one way to constrain the matter content of the theory is to consider some energy conditions. So they capture the idea that matter behaves in some physically reasonable way, and they are important because they appear in the proofs of some fundamental results in GR, such as singularity theorems, also laws of black hole thermodynamics, positive mass theory, and so on. And there are four mostly used ones. First is the dominant energy condition, which will state that the flux of energy momentum is causal. Weak energy condition basically says that the energy density that an observer is measuring is non-negative. Null has the same form, but for a null vector L, and it's often represented in its so-called geometric form. So using Einstein equation, you express it in terms of Ricci tensor. And then basically it will say that the null congruence is converging, and it is important in the proofs of singularity theorems. And lastly, there is a strong energy condition, which states that this combination contracted with future directed time-like vector fields will be non-negative. Also, it's often represented in the geometric form, so in terms of Ricci tensor, and then it says that the time-like congruence will be converging, so it's also useful for singularity results. And these energy conditions, they are not independent. They are related by the following implications. So dominant implies weak, weak implies null, and strong implies also null. For NLE theories, energy conditions translate into some inequalities on LF and trace T. So we'll say that the energy momentum tensor satisfies null energy condition if and only if LF is less than or equal to 0, dominant if and only if LF is less than or equal to 0, and also trace has to be less than or equal to 0. And strong energy condition if LF is less than or equal to 0, and trace has to be greater than or equal to 0. Now you can see that Maxwell's Lagrangian will trivially satisfy all of these conditions. Its trace vanishes, LF is just -1 over 4. And also one can show that Born-Infant Lagrangian will satisfy both dominant and null, and Euler-Heisenberg will satisfy them if invariant f is less than or equal to this constant factor. Now, another novelty compared to Maxwell's electrodynamics are stealth fields. So they got their name because they will not contribute to the right-hand side of Einstein's equation. So the fields themselves will be non-trivial, but the energy momentum tensor will be 0. And this is not something that is unique to nonlinear electrodynamics. Examples can be found with scalar fields as well. But here, in the context of Anneli theories, we will say that the field is stealth if two form F is non-trivial, but energy momentum tensor vanishes. And this will be possible if and only if both LF and trace T vanish. So we can see from the form of energy momentum tensor that if you put LF and trace T to 0, we get T equal to 0. And if we want to prove another direction, so if we set that energy momentum tensor is equal to 0, then of course this trace will be also equal to 0. And we are left with LF times Maxwell's energy momentum tensor equal to 0. And now, since such fields are absent in Maxwell theory, we have to put then LF to 0. And such fields will leave their imprint in Kummer charges, so they will contribute to the electric and magnetic charges Q and P. And also, it's important to say that not all NLE theories can accommodate such fields, because not all of them, LF will not have zeros for some theories. Yeah.
It's because the stress energy tensor is the concept of matter and energy. In this case, it's energy due to the electromagnetic field. So, uh, where is the signature of the energy, for instance, contained in the electron or magnetic field? Because the stress energy tensor is 0.
Yeah, but still, the fields themselves will not be trivial. So they will not affect space-time metric, but still, um, I'm not sure if I answered the question. Yeah, not all NLE theories will actually have will be able to accommodate such fields. And one example are null fields in power Maxwell case. And now, since they do not contribute to Einstein's equation, of course, they can evade some no-go results. For example, no soliton results that we'll discuss tomorrow, and also the theorem on the absence of null fields in static spacetimes. And so in Einstein-Maxwell theory, the possible black hole solutions are limited by some uniqueness results. And here we have different NLE theories at disposal, so one can construct various black hole solutions. So here I focused on the exact black hole solutions. I put them into three groups. So first are static spherically symmetric solutions. So here we have examples of singular black holes, such as the ones that emerged from Born-Infeld, Euler, Heisenberg, and Modmax theory. And also there is a family of regular black holes. Then in the second group, I put stationary axially symmetric black holes with non-vanishing angular momentum. So those would be solutions analogous to Kerr-Newman black hole. But so the thing is that for now, there is no example of an exact rotating black hole solution that emerges from NLE theory that is a function of invariance f and g. So if you look at the papers, you might find the discussions of rotating black hole solutions, which come from Newman-Yanis algorithm. But the thing here is that black holes constructed in such a way, they will not solve the Einstein-Anneli equations of motion. So they are not actually solutions of the theory. Also, what is sometimes done is that one imposes the metric function and then just interprets the right-hand side as some NLE energy momentum tensor, and then reconstructs the NLE Lagrangian from it. But then you will have the Lagrangian, which is written as a function of coordinates. And you will not be able to write it as a function of invariance f and g. So the question of obtaining a regular solution in NLE theories is still open. And all the standard tricks used to derive Kerr-Newman black hole, unfortunately, generally fail in NLE case. And as the last group, I put multi-black hole spacetimes, which would be similar to Majumdar-Papa-Petrov solution or the non-extremal case, so multi-Reisner-Nordstrom black holes. And here we managed to construct an example of such a solution in Modmax theory. So in the extremal case, the solution is actually isometric to Majumdar-Papa-Petrov solution, so it has no conical singularities. The gravitational and the electromagnetic interactions are exactly counterbalanced, but there is the important distinction compared to Majumdar-Papa-Petrov solution, and that is that the extremality condition for each black hole is now modified by charge screening effects. And of course, in the non-extremal case, conical singularities are present. And now we can sum up with this table, which compares some basic properties of Maxwell theory and the general NLE theories. So Maxwell's Lagrangian is proportional to invariant f, while NLE Lagrangian can depend on both invariants f and g. And such theories can obey Maxwell's weak field limit, but also there are examples which do not. The equations of motion in Maxwell case are linear. In the NLE case, of course, they're not, and we have seen that the nonlinearity is manifest in this two-form Z. Maxwell Lagrangian is invariant both to conformal and SU2 duality transformations. while a general NLE theory will not share these properties with a Maxwell case, so only if the Lagrangian satisfies some additional constraints. Maxwell energy momentum tensor satisfies all of the stated energy conditions, while NLE theories may violate them. And this will be especially important when we'll discuss regular black holes, because this is one way of evading singularity theorems. So the phenomenon of birefringence is not present in Maxwell theory, but in NLE case it can appear. Self fields also do not appear in Maxwell theory. So if the energy momentum tensor is trivial, then fields are also trivial. While in the NLE case, certain models may accommodate such fields. And also we have seen that in Maxwell case, black holes are not regular, while there is a possibility that we could, using classical fields, regularize black hole singularities if we couple gravity with NLE matter. And that is all for today.
Questions? Thank you. Thank you. So I was wondering, you say that there is no exact solution for a spin-in black hole in nonlinear electrodynamics. Does it mean that there are numerical solutions instead that were found through, I don't know, some simulations or whatever?
To be honest, I am actually not sure if there are numerical solutions. Yeah. So usually I'm working with the exact solution, so I'm not really familiar with numerical, but there might be some. But I cannot say for sure.
Thank you very much. Any other questions? So let's thank Anna again.